Hello, everyone. Thanks for joining us. Gosh, it's great to have so many people here. I'm excited to get started. I was going to say hello in the chat and let us know where you're joining us from, but it looks like everybody's gotten a head start on that, so that's great to see. Welcome. So good to have you here. Got someone from Svalbard. So I think we're going to need to see a little bit of visual proof of that. So if you're not already in our Discord, I think you need to head over there and give us a little proof that you're actually at Svalbard. It's a place I'd really like to go. If you are there, sun's not setting these days. A lot of folks from the US, I'm sure. If you're watching this because you're in a time zone that wasn't amenable after the fact on demand, welcome to you as well. Sierra Leone, excellent. All right, good to see Pittsburgh. Pittsburgh's always the least exotic or fun of any possible location anybody says in the chat. Germany, you're up late. Thank you for joining us. I also want to ask a question before we start, which is, if you're here, I think it's likely, it's fair to say that you're interested in making something, right? That's what we ultimately want to get to. And what we will talk about in the meantime is how we get there, right? And not just rushing into making something, because I think I'm somewhat obligated to say this as somebody who is a professor in a computer science school and talking about making something in the right way. And what we're going to talk about in this first session is making sure that we understand terminology, lingo, jargon, and the underlying model that we're even working with, where it came from, what's a little bit about the history. So we're going to get to all that. But if you're here and you're interested in making something, my next question for you is, feel free to give us an example of what it is that you would like to make. Is there any passion project, something that you couldn't make before, something that you wouldn't feel comfortable either coding yourself manually or paying somebody, a service fee who's an expert to create something? Are there examples of things that you want to make that you feel like vibe coding will allow you to generate? So let me know your thoughts on that in the chat. I'd love to see them. Also, you can come to our Discord and let us know about that too. I will show you a couple of examples of things that either I have made or people that I've worked with have made that can kind of, if you haven't vibe coded something before and you haven't seen really honestly how cool it is to make something that you just couldn't have made probably previously, I thought I'd show you a couple of examples. So one of the things that I built, sort of the first version of this, and then we worked with a couple students on, is we made a sandbox for our Programming for Lovers website. So I wanted to show this because I did want to mention, if you haven't had a chance to hear this from me before, we're going to talk about vibe coding, which means not necessarily always looking at the code itself. If you're interested in a fundamental course in programming, we have that too. You can check it out at programmingforlovers.com. And we made our own, essentially like online IDE associated with the course, because then it could be branded, and we're going to make changes to this in various ways. And, this is the sort of thing you used to have to pay a service fee to a website to do. And these days you can just kind of make it. So if you want to write a factorial function, this is our sandbox, and then we can run code in the browser and it'll give you an answer. And, in this case, we've got just a function to compute a factorial, and we call factorial a 5, and it prints an answer. Another app I wanted to show you, and I can't show you everything. There's some student data here. This one we worked with a couple students on, and we launched it today to our high school program in computational biology. So I teach a program at Carnegie Mellon to about 100 students from across the country, even around the world, in computational biology. And it's a super exciting time, but a busy time of the year. And one of the things that we introduced last year, we didn't have an app for it, but we introduced a house point system. So the students get divided. There's like 25 students in each house. And we have ACs, Gs, and Ts, and we kind of branded it and everything. But we had 3 students who I worked with to actually build out an app where we started with what is it that we wanted this to look like? What are the features that we wanted this to have? And it's nice because I can award points to individual houses. I can award points to individual students or even groups of students who do good work or who, demonstrate that they've really understood something or ask excellent questions or something like this. And this is an example from my perspective of, and when you go into the classroom, the students get just wildly excited about it. It's not something that is really something that we could have purchased. It's probably not worth paying somebody, thousands of dollars or tens of thousands of dollars, what maybe a few years ago, to make a really nice version of this application, this web app that we want to have. But it's something that makes our educational experience way better. And so it's a fun toy, but it's also something that's like really useful in my day-to-day life. And it's an example of something that we just couldn't make not that long ago. So this is why I kind of want to bring other folks into this, right? To say, how is it that we can make applications that you dream about? And it's cool to see, like, you all have ideas of that. I would say if you don't have an idea yet, you're still welcome here, right? Like, we're going to have a project period that, isn't happening just yet. And so there will still be opportunities for you to, think through this and come up with a project that you're really interested in. So that's good to see. If you don't have it yet, that's all right too. It's good to see a good combination of things too. So abstract strategy games. Mark, it's great to have you here. Roles of small molecules, we have scientific ones, flight path predictors, all good stuff. I like secondary market trackers on watches and jewelry. That's good. Exactly. So just whatever you care about, AI has kind of opened the playbook, right, on what you can make. And these are often ideas that, they just don't exist out there already. They're not like commercially viable or whatever, but they're things that can really help you out. Keep telling us what those are. Let us know in the Discord. I saw there's a question about, what is vibe coding exactly, right? Roy, that's a good question. I'm glad you asked because that was the next thing I wanted to say. And the origin of vibe coding is one tweet from Andrej Karpathy. Now, Andrej Karpathy is one of the co-founders of OpenAI and took a detour to work on education, realized that wasn't his cup of tea. Okay, it's not for everybody. Currently working at Anthropic. And he had the courage to say, there's a new type of way of making things. And I'm calling it vibe coding. And what it means is, and he's saying, I'm encouraging my laziness. I'm sort of going with the flow. Sometimes I'll hit a bug and then I'll have an error message and I give that right back to the AI too. And sometimes it can't fix something. So I ask for random changes until it just kind of goes away. And really, probably these days, what you see is the AI is getting kind of smarter and smarter as we go. So if you have a bug, you just wait a little bit of time and then the AI gets smarter and it can fix it. So this is a remarkable statement from somebody who is at the absolute forefront of the technical revolution of AI, because it's a brave thing to say that he's not really paying attention to any of the specifics of what the code is. Like, he's not digging into the bowels of the code at all. And it's also remarkable to see that this is, February of 2025. So it's only like 18 months ago that this term gets introduced. And yet I think that vibe coding as a mechanism, as a paradigm, is something that has had just unbelievably broad appeal. And the great example of that, like, I'd be remiss not to mention Rick Rubin, because I think he has been very instrumental in popularizing this, that thinking about vibe coding in the light of like Taoist meditations, and how is it that through vibe coding we can almost achieve a commune with nature and draw ourselves like closer to God, for lack of a better way of putting it. And I think that's good. I'd have you check out, this is his The Way of Code collection of meditations. There's all these little animations and then little poems. But That's not really what we're going to talk about tonight. I do think, and part of what I've been going for with kind of our caption, our screen cap that we have at the top, like our cover image, is trying to capture some of Rick's energy a bit and thinking about what we're going to eventually, when we get to our building period, that when we're making something, it's more about joy and attitude than it is literally anything else, right? Like, so when you're working with this, you're kind of freeing the soul. And I know it's, in many cases, you're going to be simply going back and forth with a chatbot interface, although how that works is going to change a lot as we go through the AI revolution, right? Like, we're kind of confined to this chatbot interface these days. But that's really what we're trying to do. And what I want to have at the end of this is a collection of really cool projects that the folks here who want to get involved with this have all built that we can kind of share with each other from the perspective of joy. And that's important for me to say because I'm not really sure myself exactly how AI is going to go on a global scale. I think it's probably clear that it's going to cause immense fundamental changes to human society. I think I'm probably sure of that myself. But what the Vibe Coding Studio is about here is to take a narrow but optimistic view of what we're doing, which is make something that is joyful and positive, rewarding to you personally, and something that you couldn't have made before, right? You didn't have the resources to pay somebody to do it because it would have been extremely expensive for something that might just be something that you want to see made. And the course on the whole, if for nothing else, it's like a way for you to find your Zen. So that's where we're eventually going to get. And if there's an end result in sight, it's that I want you to feel comfortable with sitting down, making something that you care about. So it's awesome to see all these things that you want to do. And yeah, we're all here. Let's all build them together. Now, there are a few things I should say before we're ready to get there, though. And that's the goal. In the meantime, there are a few things that we kind of need to cover. As I said, I'm a professor in a computer science college, so I'm by nature, I try to be as thorough as possible. And through our introductory lectures here, what I want to do is to say, first off, what is artificial intelligence? Where did it come from? And that's what we're going to talk about today. And there's a little bit of a disclaimer here, which is that what artificial intelligence really is immensely technical. There's an enormous amount of mathematics. And you probably have seen all the headlines of people receiving tens, 50, $100 million from tech companies because if you can demonstrate a little bit more technical expertise than somebody else, it has immense value commercially these days. So we can't extricate artificial intelligence and neural networks and this foundational stuff. We can't extricate it from mathematics. I still want to show it to you. So what I've tried to come up with here is as high level an explanation as I can that still respects your intelligence. And you might, let us know kind of what your understanding of neural networks and AI is. I'd be happy to see that. My sense is that we probably have a wide spectrum of folks who have very little experience with what neural networks are, or folks that kind of already understand the basics of neural networks. But what I want to do here is how can we bring ourselves up to as level a playing field as we can obtain without necessarily getting into a lot of math. And the one thing I want to point out too is this is still supposed to be fun. So there's no exam here. Your ability to vibe code is not a function of your ability to understand some of the math I'm going to give you in a couple of the exercises we're going to talk about around the foundations of neural networks. These are just here to kind of build your intuition and your understanding if you're interested in that and to have a better appreciation of what the history is. So don't worry if you're not super strong in math or you feel like there are some things here that are a little bit challenging. That's great. This is where we're going to start. And then the next things that we're going to look at are things like how do I use AI to learn effectively? So there was a study from some Chinese researchers actually that came out a few days ago that said if you give secondary students access to large language models and you don't try to teach them effectively how to use them, their homework scores go up, the time of homework completion goes down, and their exam scores go down. And all of this was extremely significant and substantial. And so we're entering an era where just because you have access to this tool doesn't mean that it helps grow your brain. So how is it that we can actually grow your brain using AI? How is it that we can set up like what I would call an AI stack? And especially, I'm borrowing a notion here, how is it that we can effectively get good at one particular tool? So in my case, I feel like I'm very good at Claude, and that might not be the tool that you particularly want to get good at, but it's part of kind of the stack I'm going to show when we talk about, for example, how is it that you can use artificial intelligence as like a second brain, something that you manage and something that you can offload a lot of frustration or delegate tasks to, et cetera, whatever it's going to be. So we'll talk about that as well. And then we're going to, of course, talk about vibe coding, how to make sure that you're vibe coding a project effectively from start to end. And I'll give kind of as like a small demonstration of a small project that we might make. How can we make a web application to do something in a short amount of time? Now, you're going to have a much longer period. And so then the training wheels are going to come off. You're going to have the opportunity to build something, demonstrate it to us, like as a community, and get a certificate that kind of recognizes your work here. But most importantly, you'll have a project that you really care about that you can say at the end of this, this is what I did. And I think that's what matters the most. So all of this is going to be happening in terms of our stream lectures. We're just going to be here on YouTube Live. You can watch these on demand. All that is great. The community side of things, that's why we have a Discord. And so please join that in our mailing list. And if all this sounds good and you enjoy what we're doing today, you like the idea of having a community of other learners that are making stuff too, you can join us at philomathlearning.com. That's how you unlock the certificate and the additional lectures and our project period. Of course, please, like, subscribe. If you're here live, keep the chat up. It's great to see everybody chatting. I'm going to have a couple opportunities where I can ask you questions or there may be an exercise or something. So keep going with the chat. Love to see that. If you're watching after the fact, drop a comment. All that helps us stay visible. And otherwise, I think we're ready to get going. So if you have any questions, by all means, let us know. And I think we're ready to start with some AI foundations. All right. So we're talking about foundations of neural networks. And I'm going to introduce this in a way that I'm pretty sure no one else has. And I want to tell you about a summer assignment that I had before my junior year of high school from an English teacher, Mr. Elledge. I don't think he's in the chat, but if you are, hello, Mr. Elledge. He had an assignment that he would change up every year. And the assignment was, I'll give my students a quotation from a book, and it's their job to tell me where it comes from. What's the source of it? So the quotation that he gave me was, what is this quote? Where is it from? And the quote is, so we beat on boats against the current, borne back ceaselessly into the past. Now, you may know where that comes from. The younger version of me didn't know where it comes from. And so I thought, well, I'm not entirely sure how to do research around this and figure out, I have 3 months to figure out where this quote came from. And if you know, it's actually the final line of The Great Gatsby. F. Scott Fitzgerald liked this quote, AKB, great job, you got it. You got it just under the nose. F. Scott Fitzgerald liked the quote so much that it's actually on his tombstone. So we'll talk a little more about that later. But I was reflecting on this the other day, and I just thought, especially from the perspective of education, how I solved the question was, this was the very, very early days of Google. I went to Google and I did exactly what we would do today, which is I entered this quote into Google and I got an immediate answer. So, this challenge that was supposed to take me a period of months had been shortened into a second. And I think that's a great kind of example of looking into the past and seeing kind of the moment in history that we were at there, and that it's actually challenging to even remember the ways in which we thought about certain problems. So this is an example of an exercise. I think there's a reasonable reason to give a student an exercise like this, get them in a library doing some homework and research and maybe even reading. But that was completely leveled by a new technology. So it made asking this question essentially pointless and so forth. Then we're at a moment in education where the same types of things are happening, but really they're an opportunity to kind of reflect on what are the challenges we even give students in the first place, and constantly asking ourselves, why am I doing this? Which I think is a really good thing for education. So I want you to hang on to that thought, that quote. And I also wanted to give you an analogy that might not seem like it has anything to do with neural networks, which is, imagine that you've got a droid, and the droid can roll around and take measurements of a new planet that you're studying. And you don't know anything about this planet. You just know it's got a smooth surface, so it can be explored. And you want to know, what are the ways in which you might program this droid to identify something interesting about the planet. So maybe the planet is otherwise cold, but it might have some regions that are warm enough to be inhabitable, for example. So we want to program the droid to find those warmest parts of the planet. It could be the highest or the lowest point of the planet. The point is, there is something that we're trying to find and optimize along the surface of the planet. And I want you to think about that particular question too, and you can put it in the chat. I'm probably gonna keep going here, but feel free to let us know what you think about, if you had this hypothetical droid, what is it you would tell the droid to do in order to look for the hottest part of the planet? With those two analogies kind of in the back of our mind, we'll talk a little about where the very foundations of artificial intelligence these days actually come from. And they come from fundamentally trying to study or trying to come up with a model of the human nervous system. So neurons form this large network of cells that can exchange information. So you have an electrical signal that can travel down these axons, and when it reaches sort of the boundaries of other neurons, it can exchange this signal to neighboring neurons. And so I think the typical neuron is connected to like 1,000, on the order of 1,000 other neurons. And so in this way, you can propagate a signal from one neuron to another and exchange information throughout your body. So the point becomes, how can we model this process? And the very first model goes back to McCulloch and Pitts. And this is from literally the era of World War II. So I always show this slide to students to just show the two photos of the two men and to illustrate kind of how beneficial it can be to have truly interdisciplinary work. So McCulloch was a neuroscientist and Pitts was a logician, but also the benefit of having like teams of people who have kind of different thought patterns or come from different walks of life or different personalities and so forth. So you couldn't have picked two different personas here. You had Pitts on the right as a buttoned-up logician, and you had Warren McCulloch, who was a freewheeling scientist. This is from an interview that he did later in life for television, where he showed up to the interview only with a pair of shorts and a cigarette. And it's a fun interview to see on YouTube, so it's out there. But their eventual model is to say, well, what the nervous system is doing really is inherently connected to logic, or we're going to come up with a model in which we've noticed that as it's sending these signals, it's kind of doing logical computations. And so their model of a neuron, trying to just kind of abstract away anything, all of the other details, is to say, well, each neuron is aggregating information from a lot of other places, right? And so you can think about all of this other information that it's receiving, and it needs to fire or pass on this signal and be activated if it receives enough inputs from its input variable connectors. So you might think about this. There's like a classic way of thinking about it as I'm making a yes or no decision, and I'm aggregating different pieces of information as a result of making that decision. Should I go to a concert? Well, it's a band that I really like, so that's on the plus side, but it's going to be in Cleveland and it's outside and it's supposed to rain. So all of those pieces of information get aggregated. And in the McCulloch-Pitts neuron formulation, you take all of your individual binary pieces of information. Think of these also as like lights that are getting switched on. And as those pieces of information get passed into the decision that I'm trying to make, you simply sum those pieces of information. And if the sum of the number of lights that are on when they're passed into me, if that number of lights is above some threshold, then we're going to output a 1. So my own light is going to get flipped on, in other words. And I will pass this signal on, and the neuron is essentially going to, we'll think of the neuron as firing then. So I'll give an example here. The simplest case is I only have 2 lights that I'm looking at. And if both of those lights are on, meaning that my threshold is 2, so I'm aggregating this decision from 2 input variables. If x1 and x2 are both on, then in that particular case, I'm going to output a 1. So I'm going to pass that signal on. And in other cases, I'm not going to. So I'm going to sum the inputs that I receive, the number of lights that I see on. If at least 2 are on, meaning both of them are on, I'm going to pass that on. And if anything else happens, meaning when I sum those inputs, it's not greater than or equal to 2, well, I'm not going to pass that information on. So I have 4 possibilities then for what the values of x1 and x2 are. So x1 is on in these cases, it's off in these cases. x2 is on in these 2 cases. And we sum the values of x1 and x2 in each of these cases. So there's only one possibility where when we sum them, the value winds up being greater than or equal to 2. And it's this case when we output a 1. In the other cases, we don't output a 1, we just output a 0. So the light is switched off in that case. Maybe I want to lower the threshold in this case. So maybe I'm saying that's a little bit stingy. And the threshold for this particular model of a neuron to fire could get lowered to a 1. And in that particular case, well, for these 2 instances, when x1 is on but x2 is not, or x1 is off and x2 is on, when you sum the 2 resulting lights, so to speak, it's now at least equal to the threshold 1. So in these 2 cases, you'll see that the output actually will be 1 because you're above the threshold. So here's an opportunity for me to ask you a question, right? And it's connected to a little bit of what we talked about before. Do these remind you of anything? Have you seen anything else in a different context that might connect to these 2 neurons that we looked at? The first one being when you see a threshold of 2. And so you fire only in this one particular case. And the second one being where you have a threshold of 1 and you fire in all 3 of these cases. I really like if-else statement because, yeah, we could have an if-else statement where you're checking, are 2 things true or is one of the 2 things true? Very much so, yeah. However, whether you're coming at it from the math side of things and you would call it a truth table, or the logic side of things and you'd call it a logic gate. This first neuron that we saw is representing the idea of taking an and of the two lights. In fact, I actually kind of gave it away a little bit by saying both lights have to be on for this particular neuron to fire an output of 1. So it's only going to be passing on the light source if both inputs are on, or we might think of this as true. If I lower the threshold, in this case, we could think about what's happening here as an OR of the two inputs. So we have two input binary variables, and if either one of them is true or they're both true, so if either one of these lights is on, then the output is going to be 1 in this case too. So it's wired up in a way that the only way that I will output 0 is if neither light is on. And the one way that we can write x1 or x2 in logic is often with a wedge. Okay, so if you've programmed or you've coded before, you'll be familiar with this way of thinking about truth of something, but you usually just use the word or use a vertical bar or something. So this was why you had an interdisciplinary collaboration between a logician and a neuroscientist. You can see the connections between what they're doing. You take a model of a neuron, and then they have hardwired in that for this model of the neurons are just representing truth tables of logical connectors. And so we could say, like here, this again was our and of our two input variables. So we have a threshold of 2. You only pass on a value of true if both of your input values are true, and in other cases you output a 0 or false. So what we could say is the model of the neuron is representing this truth table if, for the collection of variables that you have, the output of the neuron for different inputs matches what you would see for the truth table corresponding to that connector. So this pattern of 1s and 0s matches x1 and x2, which is written as this upside down wedge often. But the idea is that the neurons are sort of reproducing at least part of logic. Now, that's just the start. And there's another really important idea that comes from this kind of time frame a little bit later from Donald Hebb. And what Hebb said, which has later been simplified, fantastic way of simplifying it, to the phrase, the neurons that fire together wire together, is that if you have two neurons and one is repeatedly helping another neuron fire, then the connection between those two neurons is going to strengthen over time. And that's not something that is present with these McCulloch-Pitts neurons at all. What the McCulloch-Pitts neurons are really trying to do is to present, here is a rigid model of the neuron. The weights are fixed, and the inputs are only binary. And based off of the inputs that I have from each of the input neurons that I have, I'm aggregating that information, I'm just doing a simple sum, and then I have only one thing that I can do. Take the sum, is it above the threshold? If so, I fire. What's interesting about this particular theory is that this comes from this organization of behavior book, and it was purely a theory. So it actually really wasn't established experimentally for like 25 years after this, but it was a great idea that Hebb had. And so he gets to be cited always when we talk about the idea of the connections between neurons strengthening or weakening over time. This is a kind of almost going back to my example of using Google for the first time, that I think this is something that is pretty common for everybody to kind of think about, right? We think about the plasticity of the brain and the idea that you can reinforce connections and they can get stronger, right? And so this all comes from what at one point in time was simply a theory. But what it means also is that we don't have a model of the neuron, like as a logical or computational construct, we don't have that model that allows for this changing of weights or changing of connections. And so we need a model that winds up being a little bit looser. And so a very natural way of generalizing this is by allowing the weights themselves to not just be 0 or 1. So we're allocating, yes, the lights are on. And in this case, we're receiving a 1 or 0 input, right, from all of our inputs. But I'm also going to weight them. So going back to my concert example, it might be that I just love the band so much that that outweighs everything else. Or it might be that I hate traveling to Cleveland so much that that winds up being one of the most important things here. So when I'm aggregating the information before I compare it against the threshold data, I want to make this weighted decision that allows for different synapses to essentially have different weights. And this comes from this idea that these connections can be strengthened or weakened as we go. So it is a generalization of the earlier model to try and take this into account. And why this is a landmark idea is partly that, but partly because Rosenblatt, who was the young professor who introduced this idea of a perceptron, was interested in using these neurons not just as logical constructs, but as things that might be able to make a prediction. So there is an age-old question, and it can come, your data itself can come from a huge number of different places. But we have a bunch of data as our input, and we may have some of that data is labeled as belonging to one of K classes. So for example, shopper profiles on a website, that could be an example. We're going to look at an example where maybe you have images of lesions on skin and you've successfully performed biopsies to label them as cancerous or non-cancerous and so forth. So we have data, maybe some of them are classified already. And what we want to do is predict the labeling of the other points and drop each of these elements of the data set into a bucket corresponding to its class. So many, many problems in data science wind up just being an example of classification. Rosenblatt actually was interested in using his very early neural network to solve this type of question. So in his case, he had a retina, which is, these were like photocells. They were wired up essentially randomly and then in a network of connections to what were called response units. So I want you to think of your, essentially the model over here is being replicated by all these response units on the left. So you had connections and your input were images essentially that were taken on a very primitive 400 pixel camera. So it was a 20 by 20 version of a camera. It's hard to imagine, to think about a digital camera that's only 20 pixels by 20 pixels. And so the inputs were the amount that sort of each of these pixels over the 400 possible pixels, the amount of light, for example, that was detected out of all of those possibilities. So your input is a collection of 400 nodes, essentially. And then all these nodes were wired into a unit in a way that the strength with which each of these nodes was wired in was represented by resistance on the wire. So this is an unbelievably analog machine, right? It's like an electrical machine, and there are knobs that control the amount of resistance on the wire. The genius really was in saying each of the kind of response unit neurons got assigned one binary simple question. So you can see in the diagram for this Mark I Perceptron machine that there's a 1 or a 0. And so at the end of the day, it's still just firing a yes or no answer. But the idea was to hand this, as your input, it would be a photo of or very primitive photo of a card, and something had been drawn on the card. And so one of the questions you might ask is there a mark on the left side of the card? A simple question, but something that a human could answer very easily, and a yes or no question. The clever idea was that until the machine could answer the question and get it right for all of the data, or as many data points as possible, the machine could automatically adjust the knobs. So if it was getting bad answers on this labeled data set, then it could change its own values by changing the amount of resistance along these wires. And that would produce a different answer to that question. And that would allow you to make a more accurate answer on a new image. So as simple and analog as this was, it worked, and it could be represented as an algorithm. So you just repeatedly showed the machine a card. It computed the weighted sum. So it's computing this weighted sum by aggregating the resistance on the wires that go into this particular artificial neuron. And then it's firing, meaning it's lighting up a light or outputting a 1 if when you compute that weighted sum, if it's above a threshold. You compare that guess to the right answer. So you say, should it have said yes, right? Like, should the light have come on? Is there a mark on the left side of this card? And if it's correct, just move on to the next card. If it's not, the machine is able to turn the knobs to nudge the weights to make it correct. And so over time, what Rosenblatt was able to show is the machine essentially was getting more intelligent. It was getting more accurate at being able to make this simple prediction. And it winds up just being algebra. It sounds like a very fanciful thing that he was doing. But if you write out what is, like, if you look at the choices of x sub I and you have a choice of weights, all these weights that feed into my neuron, you look at this weighted sum of all of the weights times the x sub I, and you add those up, and then you say, is that bigger than or equal to the threshold? Well, all of those can be thought of as a bunch of points in n-dimensional space. So it's all the x sub I that are on one side of this line. So at some point you just get equality. And so if the weights are fixed, then the x sub I that are on one side of the line, so once you've turned the knobs and the knobs are set, then when you put your input in, you're either on one side of the line or you're on the other side of the line. So when you perform your weighted sum, it's either greater than or equal to theta or it's less than theta. And so that means that in this n-dimensional space, there is some line that's going through the data, and it's saying everybody on this side is going to be a yes to my question, everybody on the other side is going to be a no to my question, and that's because I have a weighted sum, and this winds up just being a little bit of algebra. Rosenblatt went one step further, though. He said, if there is a line that separates the data, right? And these data could be in n dimensions. Here's a simple example of data that are in 2 dimensions. You only have 2 attributes, but they could be in n dimensions. If there is a line that goes through the data where all of the positive objects are on one side and the negative are on the other. So all the things that have a yes answer are on one side and a no answer on the other. Then this algorithm will always find, and he was able to establish bounds on the number of steps even. He said it's always able to find the weights that will divide your data correctly. So it'll have 100% prediction. It's a remarkable experiment. And unfortunately, Rosenblatt died young and tragically, and he didn't really get to see the end result of kind of what the model that he had made, because other people came in and said there were a lot of criticisms of this model. And part of the reason for that was this is an example of, from 1958, the world's first AI overreaction. So I know some of you have seen plenty of people. LinkedIn is a great place to find them, who are like so AI optimistic that they just overreact to every imaginable thing. I don't know if any one of them could possibly have an overreaction quite like what the New York Times had in 1958. So look at this first. This is the opening of the article about this, where it said, the Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. That's an amazing first sentence to an article. And Rosenblatt was extreme optimist and good at selling this. So he said, yeah, it's going to be done in about a year. It's going to cost us $100,000, but it's going to be done in a year, and it's going to think just like the human brain. And it'll make mistakes, of course, but it's going to, as it gains experience, it's going to get wiser. Now, some of that is actually very far looking, right? Because hallucinations are down. The machine is getting wiser that we're working on these days. But it's funny to think, he's here literally hand wiring up his neural network. So there was a lot of criticism of this optimism, as I said, and I'll explain a little bit of it by showing you one more truth table. So the word or in English, and we're going to talk about human language is a challenging thing, but one of the ways in which human language can be challenging is I think there's only one human language that has two different words for what we think of as or. And I think it's Bulgarian, but I may be hallucinating, so you may have to fact check me on that. I often say, if you're offered, would you like ketchup or mustard on your hot dog? Well, the implication is that you could have both. And so we think in our logical sense, that's a perfectly reasonable sense of or. So if both things are true, ketchup and mustard both go on the hot dog, well, you got ketchup or mustard, so that's fine. But if you were offered to go to the beach or Svalbard for your vacation, you probably can only pick one of those two things. And so in that sense, there's an implication that both of the statements can't be true. And in that case, this is why logically we represent this concept of or as an XOR or what's called exclusive or. So the only place that this differs is in the case of the original or, you have everybody is always true unless both of the inputs are false. In the case of exclusive or, you have x1 XOR x2 is false if both of the inputs are true. So another way of thinking of this is your case of you can go to the beach or Svalbard, but not both. So the implication is that they can't both be true. And the other way of thinking about XOR is it's measuring essentially equality, or it's measuring inequality. So when x1 and x2 are two inputs, when they're both true, the light goes off. When they're both false, the light is off too. And so when they differ, it measures that they're different and the light goes on. So if we had a neuron for this, the neuron would fire precisely when the two input values differ. And that's a reasonable neuron that you might want to build, right? So I have two inputs to my neuron, and if those two things are different, I'm going to measure that and be able to pass that information on. Marvin Minsky was Rosenblatt's high school contemporary. They went to the same high school in the Bronx. And they actually, at this point in time, they were like the titans of AI. And Minsky criticized a lot of what Rosenblatt was doing and said, you're too optimistic. And here is a mathematical theorem that says you can't find a perceptron that represents this exclusive or. So there is no neural net. There's no artificial neuron that takes two inputs and that can measure whether or not they're equal. So that can detect inequality. That's an important thing to have. He said, yours doesn't have it. And I know it because you said, well, everything is fine as long as I can find a line through the data, right? So, well, the points satisfying, this weighted sum is equal to theta have to be some line. And then you have to have the points such that, you're greater than or equal to theta. Those would go on one side of the line. And then everybody else goes on the other side of the line. And, find me a line through this data that divides them correctly, because I've colored the points dark gray if the XOR is true. So I think about this is the x1 axis and this is the x2 axis. So 0 is false and 1 is true. So in this case, x1 is true and x2 is false. In this case, x1 is false and x2 is true. And in either of those cases, you might remember from our truth table, the neuron would fire in that circumstance. In this particular case, you have inequality. So this is they're both true or they're both false. The neuron's not going to fire. So the truth table would be false in those cases. So I've colored the points according to what the machine should say. The machine should say that it should try to say that, these two things are on and these two are off. And all the machine can do is draw a line through the data and say the things on one side of this are the true things and the things on the other side of the line are the false things. But there's clearly no line through these points. You can try to create a line through these points any way that you like, draw any line you see. You're never going to be able to find a line that goes through the data that puts your dark gray points on one side or your true points on one side and your false points on the other side. They don't exist. And so because of that, the perceptron is simply, it can't even represent all logical functions, let alone more complicated things. But this, of course, is just the start of neural networks. And I just used the magic word of network because there is a way of producing the output that we want. Here is the start of a network of perceptrons that will represent the XOR of our two input variables. So at the bottom, I've got a truth table that I'm going to show. So the truth table has all possible assignments of ones and zeros. You have your two ones here and two zeros and 1 0 1 0. So these are all four possible assignments of true or false or 1 or 0 to your input neurons. I'm going to have one neuron that represents the OR, and we've seen this before. So this was our old friend that had a threshold value of 1 and that had weights of 1 and 1. So when you take the weighted sum, it's just x1 plus x2. And remember that it's going to fire in all three of these cases, because in all three of these cases, the sum is greater than or equal to 1. We can form another neuron here that's called the NAND of our x1 and x2. So the logical form of it is called the NAND. As a neuron, it has weights of -1 and a threshold of -1. So when we take the weighted sum here, what you see is, well, in this case, the weighted sum is -2. It's 2 here. You're taking the opposite of these values. So you have -2, -1, -1, 0. And then you say, when is that at least equal to the threshold? The threshold is -1. When are you above greater than or equal to -1? That's true in all three of these cases. So we have one neuron up here that represents an OR. This is NAND, which is the opposite of an AND. And each of these neurons represents each of these possible cases. So this is our Y1 that's going to be firing 1, 1, 1, 0 in each of these cases. This is our Y2 that's going to be firing a 0, 1, 1, 1 based off of these four cases. And here's an opportunity for me to ask you a question, which is, do you see how you can combine the results of this neuron and this neuron into a way that will eventually output the result of x1, XOR x2? The other way of thinking about this is we're passing on signal, right? So if both lights are on, this neuron is going to pass on a signal of 1. This one would pass on a signal of 0. If, say, x1 is off and x2 is on, this light will be on, and this light will be on too. So how is it that you can combine the results of these two lights or these two signals into something that eventually will output what you really want, which is x1, XOR x2? Remember, what you really want with x1, XOR x2 is a 0 here, because they can't both be true. Remember, these are original input variables. So you would want a 0 here, but you also want a 0 down here. So in either of these cases, when they're not equal, you would get a 1. That's really close to this, and it's really close to this, but it's not quite the same as either one of them. So how is it that you could combine Y1 and Y2 together in a way that actually would give you what you want? That's my opportunity to take a little break and let you think about it for a second. Let me know what you think in the chat. See if anybody can find it. Multiply is a great answer. Unfortunately, that's not part of our model here, right? So the only thing you can do with the model is take the weighted sum. So you're allowed to set your weights. Your weights can be anything you want. Your threshold can be whatever you want. But the only thing you can do is take your weighted sum and then compare it against the threshold. All right, good to see. The answer here is to take the and. So if we were to look at our two lights and say, when this one is on and this one is off, when we and them together, you're going to get an off light. So we have seen the and perceptron already. Your input weights are 1s, your threshold is a 2. So the only way you'll pass it on is if both incoming lights are on. And so if this is an and, well, what is our sum y1 plus y2? In this case, it's 1. In each of these two cases, it's 1 plus 1, which is 2. And in this final case, it's just 1. So that is greater than or equal to 2 in these two cases. And so you're only going to turn the light on at the very end in these particular two cases. But what do they correspond to? They correspond to the exact cases of when x1 and x2 are not equal. And in the other cases, when x1 is equal to x2, we output a 0. So we are actually able to cut off the light in the right times and cut on the light at the right times to correspond to XOR. But what we really needed was the ability to link these up into layers of neurons. And that's as simple of a neural network as I can show you. Well, I'm going to talk about huge, enormous, incomprehensibly large neural networks. But ultimately, understanding the foundation of this is critical to appreciating where these things started and what they're actually kind of doing. They're trying to take limitations of what one neuron could give you and instead linking them up into these networks of things that are still able to produce higher levels of computations that you couldn't do previously. So in this particular network, these two neurons that we showed before, the OR neuron and the NAND neuron, are part of what we call the hidden layer. So they're not relevant to the input. They're not the input variables. And they're not what the neuron is firing at the end. So they're not part of the output that we see. But they're very critically important to what the network actually does. And so in this neural network, those are called hidden neurons. And the bigger the neural network, the more hidden layers of neurons you're going to have. We can generalize perceptrons further. And I want to try and bring us up to modern neural networks. But each step is not actually that big. If we look at what we call a generalized neuron these days, you still have n inputs. You still have n weights of your inputs. So you're still aggregating a bunch of inputs and the strength of that connection. And you still have a threshold in this particular neuron. So all that is the same. The only thing that's different is instead of just saying, well, add up the weighted sum and compare it against B, instead we move B to the other side. So you take the weighted sum and you subtract B. B is now called the bias of this neuron. And then you pass all of that into a function. So what this allows us to do is you'd say, well, what if the weights were really strong? Okay, so I was very enthusiastic about making this decision that I was trying to make. In that particular case, I'm way above the bias. I'm way above the threshold that I would have seen. And so I want to have an enthusiastic output. Whereas if I just barely made it above the bias, I might not be quite as enthusiastic about this yes decision that I'm going to make. So it takes away essentially completely the idea of everything having to be binary. At the end of the day, it doesn't fire a 0 or a 1. It fires a or a yay or a no. And so when we look at this, the question is, what function do you plug these into? The function should be increasing because if this weighted sum is way bigger than the bias, then this value should be large. And so when we put it in the function, it should be large too. That's our yay case. Whereas if this is close to 0, maybe we fire at like a mid value. So here is one particular commonly used function historically called the logistic function. So if the weighted sum is equal to the bias, we fire 0.5. That's our mid answer. Okay, that's our meh. And as this sum gets much larger than the bias, well, this is going to become much larger than 0. So as x gets bigger, the function value corresponding to the y-axis is also going to get bigger. And as it becomes more negative, well, you're also going to fire a lower value. So if when we perform this weighted sum, it's like when we've aggregated this decision, the weighted sum is not very big, then we want to fire a value that's closer to 0 in that case. And in the case of perceptrons, I might say, like, what was the activation function we were using there? It turns out there was an activation function. What was it? Fedor says uniform. I think that's close. It has a specific name. In the previous case, we were only firing a 1 or a 0. So if this weighted sum was above the bias, then we would always fire 1. And the bias in that case was theta. If it was smaller than it, then we would always fire 0. So you only had 2 possible things that you could output. So if you only have 2 possibilities, you have what's called a step function. And so the step function is going to output 1 if you're above some value, and that was that theta that we looked at before. It's going to output 0 if you're less than it. So this was, we took these weighted sum of things. Even though it's simple, modern machine learning models have gravitated away from this logistic function and actually towards something that's closer to a step function. There was a great question in the chat about, that logistic function really doesn't replicate biology at all, and the step function seems to be quite a bit closer. And so what we've seen is the artificial networks themselves, too, have actually taken a step back towards biology. And so you much more commonly see rectifier functions. So not quite a step. So you're still actually going to be able to fire something along a spectrum of values. But if you're beneath a particular threshold, you're just going to fire 0. And if you're above the threshold, you're going to fire something that's linear. So if I exceed the threshold by a factor of 2, or if I take my weighted sum and I subtract the bias and I get 2, the neuron will fire 2. If I get 20, it will fire 20. So we're going to say it is simply the amount that you go over the threshold by. And that winds up being useful mathematically as much as anything else. So it's nice because it's simple, which means if we can talk about something called mechanistic interpretability, meaning you can go in and study the individual neurons that constitute, or individual collections of neurons that constitute a big neural network, and you can say, this is what this particular neuron is responsible for. If that's the case, something like a logistics function makes it just much harder to study individual components of a neural network. A step function is going to be tough because it's not differentiable. I'll say something very brief about that. You have this discontinuity, and you have a little bit more information here with being able to measure exactly how much the neuron is firing at that point. So it just allows you to study the neurons specifically a little bit better. The great idea, and I don't think that this is a complicated one, is if hidden layers of neurons are good, they can make our machine more powerful, it can make better predictions, and it can replicate functions that we couldn't replicate before. Let's just add lots of them. And this was something that I think people perfectly well understood, that, for example, if we are solving a classification problem, we could have a k output neurons corresponding to each of our classes that I care about. You could divide up the data into a collection of input neurons. And then you could feed all those neurons into this network with huge numbers of hidden neurons and connect them in complicated ways. And then make the machine kind of figure everything out. So by changing the weights and the biases in all these huge layers of hidden neurons, eventually the machine would get smarter and smarter. And we can just add a huge number of them. And then the machine is finally able to tune these weights, change these biases and thresholds, and then be able to output what it wants. We're going to talk about that more here in a little bit. But the problem here is training the network. And this is something that was, I think, quite obvious. So my own anecdote was at the original department head that I had for at my job at CMU in our department, the founding department head of computational biology, Bob Murphy. He had a story about, when he was a PhD student, and this is like the late 70s, early 80s, he thought neural networks were fascinating because we have this artificial version of a model that's replicating, how our nervous systems are actually connected. What could be more fascinating than that? And you're aware of what Rosenblatt had done and the conflicts and so on, but the hope of connecting all these things into these huge networks and be able to do something. But that was right in the middle of what has become known as the AI winter. And the reason why is because the hope of what the neural networks could do was high. But the realities of the computational power that you had access to were very stark. And so what artificial intelligence designed neural networks could actually make predictions about were all very, very simple. It was very challenging to move beyond a very simple binary prediction around punch cards that you're taking very simplistic photos of. So it is a beautiful, elegant idea, but that's all it is at this point in time because it's not actually clear that this is ever going to go anywhere. It turns out it very much does go somewhere. And when you fast forward, a few decades, there was a cold spring rainy day in Pittsburgh where my office phone rang. And I like to say a professor's phone never rings. Professor's office phone never rings. And that's been the case for a long time. And it was ringing and I thought, well, I should pick up because it never rings. So it's always going to be fun, whatever this is. And it was actually a local dermatologist on the other end of the line. And he said, I've been talking to my colleagues and we look at images of people's lesions, or we just look at lesions on their skin, and we've realized that we don't know a thing about being able to classify whether or not this is cancerous. Like we just biopsy everything. And do you know if you work in a school of computer science and computational biology department? Do you know anything about this? And I was like, well, this is not exactly my area of research, but remember, going back to Mr. Ellich's English class, I am good at Google, so I looked it up, and it turned out that this paper had literally just been published. And the paper here, I'll maybe say a little bit more about it. But this particular paper came from a Stanford group. It's had tens, like 50,000 citations in 10 years because it was one of the first examples of a neural network that was able to beat a doctor at making a prediction about something. And the dark secret was that the doctors aren't good at making this prediction. But there was a great hope here, which is that, you could imagine, especially in places that don't have great access to healthcare and great access to something like a biopsy, you could take a smartphone image of a lesion on the skin, and the algorithm could tell you, is this a cancerous, malignant growth? Is it benign, which means it's definitely growing abnormally, but it's not cancerous? Or is it non-neoplastic, so it's like a cyst or something? So you just are trying to classify things into 3 classes. And this was the first instance of a medical problem where the diagnosis of the algorithm actually beat the doctor. And this was really cool because it applied to all different types of light exposure, all different types of skin tone, different brands of smartphone. They were always able to beat the doctor, but the doctors get this right 2 out of 3 times. And the first version of this model, which was the front page of Nature with the absolutely abhorrent title, Lesions Learnt, just a dreadful pun, it got it right about 70% of the time. So it does beat like the best dermatologists in the US, but neither one is particularly good. And yet it's very impressive. So ultimately, it is a machine that is just turning dials, except the dials are no longer analog, they're digital dials. And the output are going to be the 3 neurons that we would want to fire. So it's according to the category. So the idea is at the end of the day, I'm going to feed in an image somehow into this huge neural network. And at the end of the day, one of these 3 lights is going to get flicked on, corresponding to non-neoplastic, benign, or malignant. The inputs are some way of taking the image and converting it to a vector or a way of pushing this into X sub I. And so actually what's amazing about this is like 50 years after Rosenblatt, 50 years plus, all they did for their inputs to the machine was take pixel intensities. So we have values x1 to xn, and each one of those values is the red, green, or blue intensity of 1 pixel. So if you think of, I've got my image of my skin, 1 pixel of that image has a red value, a green value, and a blue value. Each of those 3 things corresponds to 3 neurons, one of 3 neurons. So you take your image, you can, very classic thing to do, you convert its pixels into numbers, and then those become your inputs. So you have a bunch of different data points. Each one has a different collection of lights that are getting switched on and off with different intensities. The magic of the machine with all of its weights and biases, when you feed each of those things in, at the end of the day, is going to fire a light of B1, B2, B3. In fact, more than one of these things may fire, and they're going to fire not 1 or 0 values. Remember, we're now firing these continuous values. So what you would absolutely love to see is that for a given data point, the output neurons, I'm going to call that P of X. And what we would love to see is like, if this is a benign image of a lesion, we want, at the end of the day, somehow, we want to change all the weights and biases of all these hidden neurons in such a way that when I feed a benign image into it, what falls out the other end is basically something that's very similar to off, on, off. So only the neuron corresponding to the output of benign should have a value close to 1. The other 2 values should be close to 0. And you'll notice I'm going to call whatever these 3 values are, which we say is P of X, it should be similar to 0, 1, 0. It's not going to be exactly equal to 0, 1, 0, because remember, we're no longer doing like binary logic, right? So we're going to have a lot of freedom. The idea is, if you think about, always go back to Rosenblatt's machine, because this is the seminal idea that you have all these knobs that could get changed, right? Except the knobs here are all the weights and biases of all of the neurons that are present there. So the problem that you're actually solving is you've got your data that you're feeding in, and you've got your neural network. And what you really want to do, and this is, I'm trying to give a high level, like a simplification of this, is you're trying to change all of those knobs so that at the end of the day, the prediction, P of X, that is being made by the machine is very close to the correct label vector. So if it's a benign image, its correct label vector would be 0, 1, 0. So a 1 for the benign case and a 0 for the other 2. So what we want to do is, for all of the things that we already have access to knowing, so we have images of things that the doctors actually did perform biopsies of, we're trying to change all the knobs and weights and biases to match those known ground truths. And that is a challenging enough problem because you have so much freedom in what you can do. And I wanted you to think about the droid rolling around a planet. And this is the exact same idea. So we still have an optimization problem. The droid is still going to explore a collection of weights and biases, except it's not rolling around a planet. The droid is rolling around a hypothetical abstraction of a planet where moving in different directions means changing the weights and biases, changing those knobs associated with how the strength of decisions is getting fed forward in that network. And so what we really want then is to say, changed all those knobs so that the correct label matches the prediction label, right? So L of X and P of X are as similar as you possibly can get. And you can get very precise and formulate what you mean by saying, over all of these input data points, I want the correct label and the prediction label to be as close as possible. So I want to take an average distance between those over all of these labeled images that I started with. And I want to change the knobs so that those become very similar. That's called the error. So this average distance between the ground truth, what you would hope the machine would fire, what lights you want it to turn on for this data point, and what it actually fired at the end of the day. So what is it that these neurons actually output? That average distance is going to be called the error. And we're not going to get into the specific formulas and so forth, but what we want to do is minimize that error. And it's still ultimately this idea of local search. But again, we're not rolling around on a planet. We're going to be exploring a planet, so to speak, but the planet is all of the different values of the knobs that we can change. So for a given neuron, it's what is the bias of this neuron? That bias is changeable. What are the weights? These weights are changeable because remember, if we're saying the nervous system has this plasticity or things that fire together, wire together, well, that means that these weights can change over time. So we're representing that idea with a model, and those are the knobs that we're changing. So with the droid, it's easy to see what we do. We drop the droid in an arbitrary spot. You can kind of just go ask somebody how they'd solve this, and everybody always says the same stuff. Yes, there are fancy approaches. I saw like simulated annealing in the chat and stuff like that, of course. But even that is not that much different from just drop the droid somewhere, look around you, see if you can move somewhere hotter. And if you ever find a point that's kind of the warmest point around you, then just stop. And you might have found kind of like the warmest point on the island of Svalbard. So that would be bad. That's not necessarily a very warm place. So you want to start the droid somewhere else, and then you repeat until you do this a bunch of times, and then you take the best place that you found. That's hard for neural networks, though, because, well, for one, you don't have the visual, right? We're going to start with this arbitrary choice of parameters, values on the knobs, and then we're going to change the knobs, but we want to change the knobs intelligently. Like we want to move the knobs so that we improve the most. It's analogous to the droid moving in the warmest direction. And we're going to do the same thing. Like once we stop, the parameter changes don't have a lot of effect on the results. We're not going to change the parameters very much. And then we're going to change the parameters of the system and repeat. So you have a huge number of possible places you could drop the droid, right? So you have a huge number of collection of different weights and biases that you could set at the very start of this. But once you start the droid somewhere, start this process, the hard part is figuring out what the best direction of movement is. So how is it that I would figure out like moving in the direction of greatest improvement? And I know what that means. It means I want to reduce the error. We talked about the error being this difference between the correct vector label and then the prediction that is applied by the network, right? But how is it that I reduce the error? I want to move the weights and biases, change the knobs so that the error keeps going down. That would be good. That's what I'm trying to do. But it's not clear at all how to do that. And in particular, the hard part here is called credit assignment. So if I think about, and I've got a topical example here, which is we currently have the World Cup going on. And if you imagine, you see a goal happen in the World Cup and you think, why is it that this goal happened in the World Cup? Well, it was the result of, the goalie took a bad angle on the play and there wound up being a goal scored. But that might not necessarily be the full story. The goalie might have been out of position because there had been a turnover, and before that, another player had been out of position, and there's sort of an effect, knock-on effects that had happened, a minute previously that actually caused the chain of events that was the big indicator that led to this goal being scored. And that analogy is actually useful for neural networks because we want to change all these weights and biases along this huge network. We want to turn all these knobs and get it so that at the end of the day, it somehow miraculously has fired, you know, a value of something that's close to 1 for its correct class and something that's close to 0 for everything else. And so we're changing the knobs until the error goes down and to make that true. And if we wanted to try and play around with this and try and move in different directions, it's actually really easy to look at the end result. Like right before the goal happened, we'd be able to explain how the goal happened. So if you change these weights and biases that go into the final output nodes, well, all of this is fixed. So none of this has changed. So it's almost like you really only have one layer. And at the end of the day, you feed everything in. And if you're changing all of this, then it's very close to the prediction that you're making. So it would be easy to be able to identify what actually is going on, right? So to figure out how changing those weights and biases produces a change in what actually is going to get switched on at the end of the process. But it's hard to check how the hidden layer parameters wind up affecting that error. And the most ludicrous form of this is, I want you to imagine, right? If you're a droid, you can just roll around and explore. But imagine that you just want to change one weight. So this is like one synapse in our artificial network. If I'm doing pure local search, I would just say, well, how much does changing this one particular weight of this one edge in this one layer connecting these two neurons, how does that actually change the error over all of the data? And does it have a good effect or a bad effect? Does it decrease the error? Does it increase the error? And that would allow me to explore, because if it decreases the error, great. Okay, maybe I want to continue, decreasing that edge, and then I'll do something similar to the other things. Now, the issue here is it doesn't take global information into account, and I would be doing this one edge at a time. To say that doesn't scale is an immense understatement, because the real networks that you're going to work with here have millions, billions, even trillions of parameters. So the edge weights and the biases are on this enormous scale. And so if I'm just measuring the change of one edge at a time, this is not going to scale. The brilliant insight, which often gets attributed to Hinton and some colleagues who really just found a Ph.D. paper from like 1974, is 12 years previous to the work that they were doing, there was a Harvard Ph.D. student who figured this out and who said, yes, I know this, but actually if you think about just flipping all the edges around and you start with the output, I'm going to start with what I know is easy, and I can determine how sensitive the error is to, like the end of the soccer play, right? So what happened right before the goal. But then I can go backward in time and I can factor, yes, once I know that, what about the preceding plays associated with this? So in terms of the weights and biases, once I have this information, it actually winds up being like multiplicative, and I can determine how much each of these weights and biases factors in to the error. So how sensitive the error is to changes in all these layers. And we're not getting into the mathematics here, but this idea of backpropagation is you can start at the end and you can work your way backwards through the network and be able to figure out how sensitive the error is to each individual knob along the entire network. So it's a genius idea. It's very mathematical. And I said it's mathematical. It's because the whole thing depends on something that you would be very surprised by. BZ says it's calculus actually. That's right. It's calculus actually. And I'll let you go, and there's some great books on this. We should have. I'll send around some details if you want to take the mathematical deep dive here. It is the only real world actual application of two things from calculus, if you're a calculus fan, that you're like ever going to see. It winds up just being the chain rule of partial derivatives, something that you just learn about is this thing that's like written in stone tablets by Isaac Newton, right? But the key point is the chain rule applies, and it allows you to determine a partial derivative, which all this expression says is when the error changes, how much is that attributable to this particular weight? So for every single weight in your neural network, you can go backward through the network and determine how much this weight actually affects the error. That's an immensely powerful thing to do, because for many of these weights, it's like, no, that weight's not that important actually. But in some of these, it's really important. So what should you do? They tell you which direction to go. So you should be changing the weights that have these big values of these partial derivatives. You put all those partial derivatives in one place, that's called a gradient. This is another thing that I learned about in Calculus 2 and thought, well, that doesn't have any application to anything. They talk about it. There's a nice visual thing of traveling up here, and it does have applications in engineering and certain aspects of physics and so forth, but not really anything that I've used in my mathematical or computational biology life. But you think about, I'm traveling up a slope and I'm looking at the steepest direction of the slope. And that's what the gradient is really telling you. You could have a lot of different variables that you could take into account, right? But like, this is the direction along all of the variables that's going to give you the greatest increase. And so if you find that, it tells you where the greatest change in the error comes from, that there are some weights, there are some knobs you can turn, like in this immense machine. And these are the ones you need to change in order to give you the greatest increase in the error. And it winds up just being a simple rule, like take that partial derivative, you get a new weight, and change it by a small amount times the partial derivative. And that's everything that was there. And that's this beautiful PhD result from 1974 that's revived in 1986. And yet what happens? We get another AI winter. Maybe a trendier AI winter according to modern trends, but nevertheless another AI winter. And it's not because people don't think this is cool, and it's not because people don't recognize that you could, in theory, have this amazingly intelligent or seemingly intelligent machine, right, that would be able to make predictions and categorizations just by doing the chain rule a bunch of times and ultimately like beating a doctor at a prediction. It's not that people don't appreciate that that's possible. It's that there are two very, very practical, very enormous problems with it. Problem number one is basically what we said before, which is neural networks are going to take enormous amounts of computational power in order to train them, in order to change all those knobs. Remember, you're landing the droid somewhere on the planet, and then you're exploring. But you have millions of parameters, billions, trillions of parameters, which means you need a lot of different starting points on the planet. And each one of those starting points is going to require a bunch of mathematical computations. Ideally, what you could do is have a bunch of machines. All those machines could be responsible for like some part of this computation, and then they could combine forces. And that's the inherent power of parallelism and why parallel programming is so inextricable from the AI revolution, which means that GPUs and NVIDIA, the world's largest company, are also inextricable from the world's AI revolution because, in large part, these GPUs give you the computational power that you need in order to train the model. This is, of course, a non-AI generated selfie of me and Jensen. And then there's a second part of this too, which is you also have to have data. So you have to have compute and you have to have data. And it's very hard to train a model and change those weights if you don't know the ground truth that you're trying to get to. Remember, for our cancer images, that benefited from having trained data or labeled data where you had a biopsy and you said, well, we know the actual answer for this particular image, and that will allow us to change the weights and biases to match it for that image, and then try and test our model on another collection of images and make sure we have an overfit and that we are making good predictions in those cases too. So we simply lacked huge labeled data sets, especially for things like images. And here's where something like ImageNet from the early 2010s was immensely helpful, because the researchers behind ImageNet literally paid people. They used a lot of Amazon's Mechanical Turk. They literally paid people to look at images and hand label what those images were. So they're a huge collection of different objects, different animals and plants, etc. And so what is this object actually depicting? Hire a human to do that labeling. And it sounds like a simple thing, but it led to this enormous improvement in the state of the art. That there's this paper from Krzyzewski and the Hinton lab that essentially shows that a certain type of neural network, these deep convolutional neural networks with many, many, many hidden layers in them, had this immense performance on accurately identifying what is this a picture of. So you finally had the compute, and you finally had a huge database with many images of a specific type. So that resolves the second image, or the second concern. So we have compute and we have data. And I think there was a sentiment like, well, if we can do images, we can kind of do anything. And that was very much not true. So it turns out that image recognition was kind of easier than I think a lot of people thought at first. And that's because there's a lot of inferences that are actually kind of transferable. So if a cat's face, for example, is at a certain angle and we're seeing one side of the cat's face versus the other side of the cat's face, it turns out that these CNNs can essentially learn to have certain neurons that are responsible for being able to identify like a cat's face in an orientation, or in general, a face in an orientation. And so there's all these repeated patterns, and all of the images that are of cats tend to have similar attributes in some ways. Some of these cats look more similar than others, but our brain is really well trained to see these images of cats and be able to very quickly identify that these are all in fact cats. And the same thing applies for neural networks. So you can imagine there is some collection of weights and biases and some very, very clever way of designing a huge neural network in order to give you a prediction that correctly identifies, it fires the cat neuron for these images. But language, ironically, is much harder. So even though images seem like a much larger data set, the data seem to have will require larger storage, for example. Language is an inherently harder problem to train a model to be able to figure out. And that's for a few reasons. So number one is that context and distance matter. So, for example, the final sentence of a novel can provide deep meaning to its beginning. We look back at F. Scott Fitzgerald's final line of The Great Gatsby. So we beat on, boats against the current, borne back ceaselessly into the past. And it makes the whole book make sense, because this is ultimately about the fact that Gatsby, can't escape his past. Who he was before a certain point in his life has defined him for his entire life. And it's this grand statement about humanity and the fact that we can't keep running away from who we were in the past, right? And so that final sentence kind of wraps the entire novel together. And that's a complicated thing about humanity. There's also huge amounts of ambiguity. So according to the Oxford English Dictionary, they know a lot more about the English language than I do. The word run has 645 different meanings, depending on context. That sure is a lot. The word cat only has one. And there's also infinite composability. So I would love to give it a try in the chat. Let me know your infinitely composable sentence, which is, it's not hard for you to make a sentence that has never been uttered before, but that also is easy to understand. So mine would be, these pencils that I cooked don't taste very good with bechamel sauce. I'm pretty sure no one has ever said that sentence, and yet you understood it, right? You can see me cooking the pencil, you can see me eating the pencil with bechamel sauce and not enjoying it. So you understand what I'm trying to convey to you. And I doubt that anybody has ever actually uttered that sentence before. That makes training a model really challenging, because you now have all this kind of new context and creative stuff that the model doesn't necessarily understand. So yeah, let me know your infinitely composable sentences. But this all goes back to Turing and knowing that language is hard. And I think Turing kind of correctly, in some cases, knowing that language would be hard and devising a test that would say, once we truly have an artificially intelligent machine, how is it that we would be able to demonstrate that it's intelligent? And this test, I don't think in these days necessarily has aged that well, but the idea here is that, can the machine display intelligence via language? So if you place a human responder talking against a computer or a human, are they unable to determine, when the computer is speaking to them and when the human is speaking to them? This goes back also to something called Eliza, which is, we talked about the fact that AI optimism and people who are vastly overclaiming what their model can do is nothing new, and goes back to Rosenblatt. And also what is not new is falling in love with the chatbot. So this is something that goes back to Weizenbaum's work in 1966, where people who worked with this mock psychotherapist and chatted with it often became entranced. And Weizenbaum's assistant, I think, would lock herself in her office and chat to the chatbot for a lengthy period of time. So if you haven't seen Eliza before, it's a way of attempting to mimic therapy. And there's a trick here, which is that regardless of what it is that you say, the mock therapist essentially kind of springs back to you a consummation of what you're saying. So here is something from our infinite composability. I guess I could say that my problem is a lamp in my fridge cooked my breakfast while I've been watching a stream. Breakfast while I've been watching a stream, say yes. I'm sure, I think. And this goes on and on. So Eliza just kind of validates what you say and then tries to make connections. Now it's easy to see that it's not, by modern standards, it's kind of hard to fathom, much like it's hard to fathom going back and trying to spend 3 months in a library identifying the source of a quotation from a book. It's hard to fathom that somebody could look at this and then be enchanted by it for a period of hours, because we appreciate what's going on these days. Although I think maybe we'll look back at the current era of chatbots and people falling in love with them as kind of the same type of thing. But I think they're also much more advanced. AKB said Weizenbaum was shocked that people thought this. Yeah, that makes sense because he made it, right? And he kind of could see into the bowels of the machine. But I think it has a lot of relevance to today's era too. So all this is known. Language is hard, and nevertheless, chatbots have been around for a long time in some form. But the main advance here is one paper from 2017 called Attention is All You Need. And I mean, this has a stunning number of citations to it. And I want to give you a very high level understanding of why is this paper important? How is it connected to the frontier of AI, which in our sense is LLMs, and how that's going to help us with respect to understanding everything that we need to know in order to use AI effectively and vibe code safely. So there are fundamental problems here. And this goes all the way back to somebody trying to come up with a simplistic chatbot to defeat the Turing test, or the designers of Eliza, which is that you get a prompt from a human user and you're trying to produce a response that maximizes something. And in this particular case, it might be like maximizing the user's satisfaction with the response. And I think we can frame that maybe a little bit more intelligently as, if I have the prompt from a human user and I've started generating a response, what's the next word or even fragment of a word or punctuation or phrase or something that I need to give the user? And there's two ways of looking at that. It could be maximizing the user's satisfaction. I will frame this a little bit differently here to say it's really the word that's the most likely. So that allows us to say, yeah, now we're just doing math. So there's going to be some probabilistic distribution that says what's the most likely next word based off of what the human has prompted me already and what I've started to generate. So that's a simple thing to do, which is just give me one extra word or one extra piece of punctuation or word fragment or something. And yet, if you solve that problem well enough, you can create an unbelievable illusion. You can make it seem to the user, especially if you do it fast, that the entire response was formulated all at once. So you could do it like in an eye blink, like here's an essay answering your question. And I think a lot of people don't necessarily like that. So you see a lot of chatbots that actually show you piece by piece. But you can kind of create this illusion of intelligence, as well as that the entire response came all at once with this like extreme higher level understanding. The second note I would say is this is a bit like how human speech works. Now, you might say in some cases it's not how human speech works because you might have a difficult conversation with your boss. So you plan out exactly what you're going to say or the high points that you're going to say, and you have a sense of what it is that you want to say before you go in. But I think in a lot of casual conversation, this kind of is how human speech works. You're going back and forth with somebody and you're not thinking 700 words down the line. You're essentially just forming pieces of sentences or sentences one at a time and attempting to convey a meaning that you're conveying, but you're not actually composing an entire essay all at once. So the chatbots in some sense have really replicated kind of sort of how human speech works. Here's where everything kind of comes back. So what is an LLM? What is a large language model? The large language model is ultimately built on one of those neural networks that at one point in time seemed like if only we had enough compute to do this, if only we had enough data that was well labeled, right? Maybe we could do amazing things in the future. It turns out the future is now. And what the LLMs are doing is their training data also involves, it's not just images anymore. Now it's what we call a mixed corpus across a huge number of fields. So you could have some images in there, but you also could have rich data sets from a lot of different areas. So you could have science and poetry and essentially what amounts to the entire internet. So that's the scale of the compute that we have achieved, which is an enormous, vast collection of initial data that we feed into a vast neural network. And so when I say vast neural network, my question for you is, give me a guess. I'd love to see a guess in the chat. How many parameters would you guess ChatGPT-4 used? So there is a neural network behind the scenes that got trained on a huge component of the internet and human endeavor, and sadly a huge part of Reddit, which is another story. But how many parameters would you guess it has? I love to guess 100. That would be one heck of an efficient model. Some guesses in the billions, all right, 1 billion, 3 billion, 40 billion, 5 billion. This was, again, GPT-4. We're currently on GPT-5. OpenAI very protective about the actual number here. And the leaked possible estimate is it's about 1.8 trillion. So that means there is a model. There is something that is comparable to what Rosenblatt designed. All his analog dials. It's just that the dials are weights and biases of all these artificial neurons in this immense computational construct. And there's about 2 trillion of them. And we are still going at the full speed to make bigger and bigger networks with more and more data that are getting fed into this thing to try and get these things more and more able to give a satisfactory response to a human. Now I say a satisfactory response. And it turns out that when you're solving the problem of the most likely next word or the most likely next phrase that could be generated according to everything that humans have ever said, it turns out that it often is extremely bigoted, like what actually gets generated by the bot, because it has learned from bigoted source material. And so this goes back to controls that were taken off of Grok in 2025. But this seems to have happened quite a bit throughout the last, 10, 20 years. There was a Twitter bot that Microsoft created that they were super proud of, and it was going to learn from everybody on the internet. And what do you think everybody on the internet taught the Microsoft bot? It taught it how to be a terrible person. So has to be an extra layer. And so when we talk about something like alignment or whatever, there's an extra layer to this, which is you have response continuation where you want to find the next word or word fragment that is the most likely, but most likely is not necessarily what you want to give the user and satisfy them. So you have an extra part of this where you take human feedback, fine tune the model, and then make answers that are more preferable. So they're not necessarily the next word that's the most likely, but you're giving the next word or the next phrase in such a way that the final response that you're going to give a human is preferable to the human or is sensitive and positive and all the things that you might want a bot to actually have. So making that transition from likely to helpful, super important, but even with guardrails, everything that happens here is still a probabilistic process. That's the important thing to know. And so when you say, why do hallucinations happen? It's because there's no truth that's built into this. You have a prompt and the start of a response, and the neural network is just attempting to continue adding the next word or the next part of a word to this sequence that it's giving you. And that's kind of hard to even get your head around, right? That it's not actually looking very deeply. It is looking deeply at what it has information from you previously. So it already does have your prompt and it has the start of a response, but it really is essentially only going like one word at a time. What actually is happening is you type in your input prompt, and you might have heard the term token, right? So what I'm trying to do in part here is bring you up to speed in what do a lot of these terms that you've heard, what do they actually mean, right? And how do they connect to things that people were coming up with in the 50s? You type in an input prompt to a chatbot, and it gets tokenized. So it gets converted into tokens. So all of the words you typed gets converted into little chunks. So those might be words, they might be prefixes or suffixes of words, it might be punctuation like an exclamation mark, it might be in the word strawberry, it might be separated into one token is straw and the other one is berry. Each token itself then gets converted into a vector. Why? Because, well, we're working with neural networks, right? So neural networks have to have input to them that is a vector, just like Rosenblatt needed to convert his primitive digital images into a collection of 400 items, just like when we were looking at skin lesion images, every pixel gave you 3 values. All of your tokens get converted into vectors, and these vectors are given to what are called attention heads. So the attention head receives over this extremely vast network. The attention head doesn't get access to the whole network. It only gets access to some subset of the network parameters. And how those network parameters are chosen has to be done intelligently. But I want you to think about this process as the attention heads are all making mathematical calculations. We're not going to get into the mathematics, but there's a lot of linear algebra here. And you take those token vectors, and they all get a chance to weigh in to produce the first token of the reply. So when you work on something like Claude, for example, it's constantly telling you how many input tokens you've given it and how many tokens it's using to generate a response. So the token is the unit of currency, so to speak, with artificial intelligence, because each one of these steps of generating a token takes a certain amount of energy. It takes a certain amount of computation. And what happens is we keep adding the reply to the end of the prompt. The reply keeps getting bigger, and those steps keep getting iterated. So there's just this constant process of converting the prompt into tokens, converting those into vectors, doing a little bit of math, and then producing a token for you. Now, the really clever thing here is that it's not trying to assume like universal intelligence, because each attention head gets only a piece of the model weights. They only get a subset. That allows all of the attention heads to have their own, what you might call context. So you can imagine some of the model weights, if you think about the entire internet, you might get good at a part of the internet. So you might be good at the part of the internet that's like the English language stack exchange. So you know a lot about grammar, right? Or you know a lot about sports. I'm oversimplifying this, but the idea is that each attention head is like a council member that gets to weigh in on what the next token needs to be. And so you have an enormous network, but then you've subdivided, again, here's where kind of parallelism comes into play. You've subdivided the work of actually generating the next token in the response across a committee of partially wise individuals. And at any point in time, that collection of tokens that the LLM has access to is called its context on a high level. What that means is the more prompt that you have, what you would love to have is for the LLM to be able to take a very long prompt from you, and not just a long prompt from you, but to be able to go back and forth and to be able to take all of that information that it has received from you throughout a lengthy chat, and all of that becomes part of the response continuation problem. So it's like you have the prompt from the human user and the start of a response, but actually you could imagine that this includes a PDF that you sent it, and it also includes the 30-minute exchange that you had back and forth with the chatbot. All of that could be the context, and then the next word that is the most likely or the most satisfactory to you gets generated from the attention heads based off of all of that context. Now, that, from my perspective, is why, like, what makes everything connect, why AI has gotten better over time, why hallucinations have gone down over time, and why vibe coding can exist. Because one of the most impressive things about the growth of AI is how huge the growth in context has been. It used to be the case, and if you go back and work with GPT-1 or GPT-2, GPT-2 is a great example because we went from a 512 token context window to 4,096. It's actually a pretty big jump. And what it meant was you kind of went from a model that was really kind of like a plaything along the lines of Eliza to something that like could seem like it generated something reasonably intelligent or poetic or something. But the problem with those kind of early GPTs was that they would then forget very, very quickly. So if you try to have a back and forth, and you may remember this, if you use ChatGPT, and it might not be 2, maybe it was 3.5 or something, when you had your 8192 context window size in terms of your number of tokens, you'd reach a point where it just kind of forgot what you had been talking about. And you'd think, well, how could you forget this? We were just having a conversation. And it's because you filled its context window beyond what it could do, and it had to kind of compress things behind the scenes. And so it wasn't able to actually access everything that you had talked to it about previously. That's where, when we actually get to a context window of 1 million tokens, now you can have a conversation with GPT-5, Claude, whatever model that you're using, and it knows all of that previous context before it's able to generate the next token for you. And as a result, that functionally corresponds to it having a much deeper memory of what you've been working on. So the point becomes, how is it that we can leverage this amazing achievement of reaching 1 million token context in order to say, well, the bot has become functionally intelligent, right? It might still just be generating what we think that it wants to hear, but that it's able to do that at a level that is practically indistinguishable from an intelligent human. So it's hard to know the difference anymore. And it allows us to make things, build things, because of its speed of doing things. It's able to make things that are far cheaper and far bigger than anything that we could do on our own. So this slide, above all else, is kind of why vibe coding can exist as a thing. We're at a pretty unique moment in history that, frankly, the people who worked on this, like going back 80 years, really could have only dreamed of. And maybe that dream is a nightmare eventually. We're not sure. But we're at a pretty amazing time where even a child can wield something that is the culmination of decades of about as technical work as it gets. So that's essentially kind of what I wanted to teach you about the absolute foundations of neural networks and AI, where all this comes from. I hope it was helpful, because really what I want to care about next is how can we take all this context and understanding about what's going on inside of the machine and put it to use. Next, how can we use an LLM to help us learn something? So if it has access to the entire internet and a lot of context to go back and forth with us on, that's probably pretty useful for us to grow our brains. And that's what we're going to see the next time we're together. So that's going to be where things start to get exciting. But the really exciting thing is going to be when we vibe code too. So thank you for spending time with us. I appreciate you taking the time. And I hope you'll consider joining us for our vibe coding studio and the project period. And come join us and make something that you love. So join us in the Discord, get on our mailing list, join Philomath so you can do one of these projects. Let's have a community of building things that we all really love. And I'll plan on seeing you next time. Until then.